Yeah. So I mean, of course, the first thing that I always think is I hope that people are finding talks every day that interest them. You know, I mean, that's one of the most important things. And of course, it's a tricky thing because we run a mainly bottom-up type science program where we rely on the community to propose sessions. And we hope that in those proposals that it kind of covers all the interests that people have, and that as a result of that they find something that they enjoy and that they can listen to and learn from. But there's always a worry, I should put it, that there's gaps, that there could be a gap, you know. And of course it's a tricky thing because when people come to submit an abstract to the meeting, they look at the program, and if they see a gap, you know, they might not submit their abstract, you know, and it's difficult to get feedback from those people because of course they're not coming. You know, they didn't find what they wanted. So what I really then hope is that those people will then think about submitting a session next year in the Montreal meeting, for example, that could then fill that gap. However, when I look at the meeting, so far I'm pretty happy. I think it does cover those most of those areas. There's of course, in addition to finding something that's interesting, what you really hope is that researchers are getting that key bit of feedback from their talks or their presentations. You know, it's really important that the scientific method is such that, you know, the results and ideas and hypotheses are discussed again and again and again. And the importance there is that there are other researchers with different perspectives that are maybe looking at the same problem but from a different angle. And the amount of feedback and information that they can then give can be radical to a project. And it's at a meeting like this that type of interaction is happening. You know, we often say to the students that, you know, you can save a lot of time in the laboratory if you read some papers, but that amount of time pales into insignificance into the amount of time you can save by talking to an experienced researcher here who has just seen your talk and has a different angle and is working at it from a different perspective.
I became director of PCIGR basically when I joined UBC in 2002. Things have changed significantly since then because I ended up being in charge the year after, and I have an idea. Yet from the beginning I wanted PCIGR to be an open facility. That is, anybody who is interested in doing research could contact us and we'll help them design research project and potentially adapt our techniques to make this happen.
So here at PCIGR, I think we're unique in Canada because we have the ability to go from a rock in the field and to do everything from mineral separation to uranium-lead high-precision geochronology to high-definition SEM imaging to any kind of trace element or isotope you could possibly imagine, which is something that really doesn't exist anywhere else in Canada and allows researchers to come here and we can really tailor-make their project and help them answer their questions with any tool you could possibly imagine, which is very unique.
My main task involves research services together with my colleagues. And that comprises providing sample preparation, chemical and isotope analysis. So right now, we're working on the OSIRIS-REx mission. We were lucky enough to contribute to the chemical analysis, major and trace elements to the program. Meteorites have the disadvantage that they're always contaminated, whether it's the atmosphere, the gas, or any other terrestrial substances. While this sample was probed directly on the asteroid, was safely contained and brought back to Earth. And we're very excited and very honored to be part of that program. And the analysis will hopefully help us to understand the origin, the evolution, not only of the parent body of this asteroid, but also of our entire solar system and other planetary bodies in time and space. So how did our solar system evolve? How did the planets evolve? How did Earth evolve?
As the world looks to particularly decarbonise and electrify, we know that that infrastructure is going to be underpinned by minerals. So we know we're going to need more minerals, and with a lot of our new technology, we need different minerals that we haven't used as much in the past. Things like tellurium in solar panels, for example. So we're seeing a shift in the types of materials that we're consuming. In many cases, we don't have great models for how those deposits necessarily form because we haven't looked for those materials in the past. And so by developing new understanding of what geological processes form those deposits, we can develop new exploration strategies. And through our research on characterizing where those minerals are and what elements are associated with them that we can do here at MDAU and at PCIGR, we can really help to address that challenge.
As a student, you normally don't get the opportunity to go through, in general, you usually don't get the opportunity to go through and process and analyze your own samples. So that in and of itself is hugely important for future careers. The fact that I've also been able to be involved with setting up the methods within the lab to even start to analyze an element that literally doesn't happen. It's a really exciting opportunity. The experience of being able to set up a method within the lab, I'm going to be able to take that with me wherever I go and be able to do that in any lab.
PCIGR has a lot of amazing facilities and instrumentation, but because of the interdisciplinary nature of the research that we do, actually interacting with a lot of the research scientists and faculty at PCIGR has been a real benefit because it's helped me to not only get hands-on experience working with instruments and in lab spaces, but also working with other scientists with different perspectives.
So I am lucky enough in that all of the research and work that I have done in labs at PCIGR have actually equipped me enough to be hired or have a job lined up post my master's as a lab analyst, which are all things I wouldn't have been able to do if I hadn't gotten experience using the mass spec machines here and analyzing things like rare earth elements and lead isotopes. So all of the instrumentation, which are all very niche instruments that are not widely available around the country or even globally, are all instruments that are very exciting for me to be able to use and are transferable to other labs across the world.
We're open for motivated students to come and join our team. We have a huge range of things to work on, and we work at the cutting edge of analytical techniques. So if you like hardcore isotope geochemistry, if you like low temperature applications, sedimentology, if you like tracking pollutants, if you like volcanoes, if you like erupting lava or mantle geochemistry, there's a little bit of something for everyone here. And it really is an inclusive environment that you can come and do good research and become better scientists overall.
I like the fact, and I worked on that, to provide a service to the community, something that other laboratories don't do. We need more facilities like this because geochemistry over the last 20 years has become a very important tool in earth science, environmental science, to document climate change, to document pollution, environmental impact, to search for critical metals. It's all related to the improvement of techniques.
It's really important for scientists to connect internationally because each of the countries that conduct science have different ways of doing it, and so when we bring those communities together, we strengthen our ability to answer really important questions about chemistry or geochemistry. For me, I'm a client scientist, and so of course I worry about CO2 cycling and how it affects our lives. Well, our different communities bring together different people. And so Europe is very focused on, well, it's not that they're focused on one thing, but they have priorities. The US has priorities, the rest of the world has priorities. So when we bring everyone together, those priorities meld and we get the best answers. Well, climate change on the lifetime of a human is all chemically driven. It's all about the reactions and the CO2 content in the atmosphere. So it's really the base science for climate.
Sure, so I'm going to be talking about magma ocean events, basically how the Earth evolved in the aftermath of the moon forming impact from a big ball of magma ocean to its present day state. I'm going to be talking about using isotope tracers and how we can use them to kind of unravel processes taking place a really long time ago, sort of within the first kind of 50 to 500 million years of the solar system. So it's really trying to look very far back in time. So I think they provide a mechanism to kind of stitch that community together. They provide a mechanism for people to learn from each other, whether that's finding out about new discoveries or whether that's finding out that everybody is experiencing the same problems that you are. I think that's incredibly useful. Obviously, you can see the latest developments, but sometimes it's also just nice to see how people individually are coping with different challenges. So I would really say talk to people. Use this meeting to build your use this meeting to build your connections. I'd say sure, go and see talks, go and see posters, but if you're in the middle of a fantastic science conversation with someone that you've just met, don't run off, just enjoy the conversation. You can always watch the talk later, you can always read the paper later, but really build your connections.
Thank you so much for giving me the opportunity to share my ideas on the plenary talk that I will be having tomorrow. I just want to set the stage by saying that within the framework of the planetary boundaries, which include biosphere integrity, land system changes, freshwater changes, biogeochemical flow, ocean acidification, atmospheric aerosols loading, stratosphere ozone depletion, climate change, and new entities, giving a total of 9. 6 have transgressed safe operating space. Of these 6, the freshwater climate change nexus is a very glaring and require close and regular geochemical observation and fixing to save humanity and other ecosystem services. Thus, my plenary discourse emphasizes the use of geochemistry to identify the undesired concentration of fluoride in drinking water in the Sahel of Africa, identify the impact of this fluoride that causes dental fluorosis on children bearing who are still condemned to consume the fluoride-rich groundwater, and to demystify the myth of witchcraft as a cause of fluorosis, because the people in this area think that every child that is suffering from fluorosis, is due to the fact that the family has some wizard and witches and all of that. So we're using geochemistry to demystify all of this and bring science close to the people. And fourthly, to change the status quo of despair to hope for total social inclusion of affected persons and engineering a cheap, sustainable, environmentally friendly groundwater defluoridation prototype filter to save the yet-to-be-born children from the untreatable dental fluorosis. Yeah, in a very few words, the biggest opportunity for geochemistry is to stand in that gap, that environmental gap problem that is created by anthropogenic, pressure and climate change forces. At this present moment of the Anthropocene, we have a lot of problems that are coming on in the environment, and we think geochemistry holds the promise, and every geochemist should stand in that gap. Whether you are a hydrogeochemist, whether you are an atmogeochemist, whether you are a lithogeochemist, or whether you are a biogeochemist. All of this in a synthesized manner, is the way forward, for a better life.
In the work that we do, we focus on reconstructing Earth's past, understanding its present workings, and sometimes forecasting the future. And we do that through isotope geochemistry. So the main tool that we use in our research group is the tool of isotope geochemistry. And that requires a range of analytical methods whereby we can extract very small amounts of particular elements, and then instrumentation to analyze those isotope ratios in those elements at high precision. A lot of the work that we do focuses on the time part of the question. So we're reconstructing events and processes that might have happened millions or hundreds of millions or billions of years ago. Those might be solid Earth processes, climate-related processes, even solar system processes, to try to add the time part to our greater history books.
Center for Isotope Geochemistry includes two lab clusters. First is the High Precision Samarium Neodymium Geochronology Lab at the Devlin Hall. It includes a clean room suite and 2 thermal ionization mass spectrometers. We also have a satellite lab that houses 2 isotope ratio mass spectrometers, an ICP-MS, and a laser ablation system. So we support both fundamental as well as applied geoscience research, and that includes plate tectonics, metamorphic geology, paleo-environmental reconstruction. The project that we have spans development of early planetary system as well as metamorphic processes spanning the whole geological time scale up to the recent human activities impact on geomorphic processes such as soil erosion, land erosion, and watershed changes.
I'm really interested in how the ocean takes up carbon dioxide from the atmosphere. Often when we think about climate change, we think about carbon dioxide being emitted to the atmosphere and the increase in the amount of carbon dioxide in the atmosphere, but we don't think about the fact that actually half of the carbon dioxide we emit today is being taken up both by the land and by the ocean. So one of my really favorite things that I get to do is send students to sea. So last year I had 2 undergraduate students and a PhD student who went on one of these oceanographic field expeditions to the Erminger Sea in the subpolar North Atlantic, to a site maintained by the Ocean Observatories Initiative. I love working with both the undergraduate students and graduate students who want to go into the field of science, to be people doing the kind of work that I'm doing, to actually directly monitor how these things are happening, do the cutting edge research, and they're going to bring that expertise to thinking about how we need to be incorporating climate change into our expectations of what's going to happen going forward, so being able to adapt to the impacts of climate change and also to mitigate the effects of climate change.
I'm the PI of Stable Isotope Biogeochemistry Lab. In this lab, we use stable isotope techniques to study the ocean's biogeochemical cycles, both today as well as in the past, and its interactions with the climate system, as well as the evolution of the marine ecosystem over time.
So I wanted to look for someone who was doing work with corals, and Tony was that guy for me, and he was doing some really cool cutting-edge work. The resources and money and just support from the department have really helped with field work and data analysis and support for all that. So that's kind of why I chose this department, and they've helped me through everything with that.
So rather than just classroom academic work, having an active geochemistry lab here means that the students get to come into my lab and generate their own data on our equipment. Students get to use mass spectrometers and X-ray equipment and learn how to generate data, not only for their own projects, but they learn how to use, calibrate, operate the instruments that we have to do their own research. And there's not a lot of places where an undergrad can come into a lab and use a mass spec.
The way I think about education is that at the end of the day, it is about learning how to think for yourself. Not out of the textbook, not about what I tell you, but your ability to be a creative, analytical, critical, skeptical thinker. And I always think of research is the perfect venue for that, because we're right on the cutting edge of knowledge. What do we know, what don't we know? And so I like to try to bring it into the classroom to help students understand that process, that dynamic of pushing forward, and how do you go forward to seek out your own information.
At Boston College, the student is our primary mission. And therefore, it's critically important that in everything that we do, whether it's in the lab, in the classroom, or out in the field, we're involving our students. And that's undergraduates, that's graduate students, getting involved in research with postdocs, with faculty, and collaborators around the world. I like to think that a laboratory like ours is really a place where people come together. It's a place where we welcome students at Boston College and our collaborators to work together.
We have grown in terms of our faculty, in terms of the research areas that we cover, and in terms of the analytical facilities that we can offer. And that growth trajectory is showing no signs of slowing down. So there's a lot of really exciting things happening here in terms of research, applied and fundamental research, graduate education, undergraduate education, and growth in our faculty and research staff. So the future is bright for Earth and Environmental Sciences at Boston College, and we encourage collaborators to join us.
From my perspective as a biogeochemist, Goldschmidt is a great and actually is a premier international event for me. So it unites a lot of different fields, yeah, from dust to environmental perspective. And of course, the main advantage for Goldschmidt is that you have an incredible, vibrant community. You can talk to many people, form about their cutting edge research.
The science program is often organized in the same way. It's a bottom-up approach. I really like to involve the community and be diverse in the topic we address, but also diverse from the geography of the people involved, diverse from the countries, the research team, and we have a very good science committee. We met in Montreal about a month and a half ago to discuss how we're going to distribute the work, who should be the best team chairs, and we're working on that. We'll have the whole committee ready for the time of Prague, and we hope to meet then.
all the different disciplines on one spot, even it's kind of a lot of people. So it actually helps to develop all the new ideas and also to expand their scientific knowledge. So sometimes it's really interesting listening to the talk from completely like different angle, different point of view is actually a discussion around. It helps you to develop and to expand your own, maybe a little bit narrow scientific knowledge.
I think the answer is obvious, the same place. So you can meet your colleagues even if it's a slightly different field of research. Everybody will think geochemistry, oh, it's all the same. Oh, and it's boring, it's chemistry. Actually, no, it's not boring at all. Applying geochemistry to climate change, geobiology, extraterrestrial projects, it's all very exciting. And when we are all in the same location, it just increases the possibility to cross paths, talk to each other. It's also very important to be in person when possible, because that increases the interactions.
Montreal makes every event feel like more, because everything about this city is so much more. If Montreal was a color, it would be a rainbow, with every shade imaginable. If it was a flavor, it would be sweet, spicy, tangy deliciousness. If it was a style, it would be artsy, classy, maybe even a little flashy. If Montreal was a vibe, it would be as chill as this, as warm as that, as playful as this. If it was a venue, it would be something that's wow, charming, unexpected, and easy to get to. If Montreal was a night out, it would be a celebration, a get-together, a moment like this. And if it was a feeling, it would feel something like this. That's why when it comes to your event, Montreal makes it more.